Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to look at Le Chatelier's principle. Le Chatelier's principle is a major component of equilibrium chemistry and is massively important. So let's first talk about what Le Chatelier's principle is all about. So in equilibrium, you have a forward and reverse reaction happening at the same time, at the same rate. Concentrations are unchanging at this point. We as chemists can put stresses on the system to cause that equilibrium to go more forward or more reverse depending on what we want to do. Now, in order to do that, we have to apply what we call a stress. Now, a stress could be something like adding more reactants or products to the system. It could be increasing or decreasing the pressure and volume, or it could be heating or cooling. Those are the stresses we're going to look at it today. Now, outright, Le Chatelier's principle says this. If a stress is placed on a system in equilibrium, the system will shift, which means it'll go to the left or the right, to the products or reactants, to try to minimize or counteract the stress that is placed on it and get back to its original equilibrium. Now remember, we've calculated K values, which are constants. Now if you're constant, that means that you have to be constant and unchanging. The only way we can actually change an equilibrium constant is through heating or cooling a system, because we're actually changing the kinetic energy of the particles. All right, let me give a real life scenario here. When you get out into the real world and you have to pay rent and you don't have enough money to pay rent one month, you have stress. In order to counteract that stress, most people would pick up more shifts to make more money to pay the rent, and then your stress comes down. So the same thing in an equilibrium system. So let's say we're looking at concentrations, okay? And I did something like add or remove more reactant or product. So let's consider this scenario. If the concentration of a species is increased, so I added some into the system, what's the opposite of adding something? Removing it. So what the system will do, it will shift to decrease that concentration. So for instance, if I added a bunch of oxygen, the system will shift the reaction away from oxygen to consume it, and therefore it would decrease that concentration of oxygen. Or conversely, if the concentration of a species is decreased, the system wants to bring that concentration back up, so the system will shift to increase that concentration. Okay, don't overthink this. We're just always trying to do the opposite thing. So if I add something to the system wants to remove it. If I remove something from the system, it wants to increase it. So if I was looking at something like heating and cooling instead, then we're always going to do the opposite thing. So if I heated up a system, it wants to cool itself down. And if I cool down a system, it wants to heat itself back up. So for instance, if the system is cooled, then it will perform the exothermic reaction to try to increase its temperature. The opposite of cooling is heating. How can we release heat? You can release heat through an exothermic reaction. Conversely, if the system is heated, the opposite thing would be to cool the system. So then it would perform the endothermic reaction and try to decrease its temperature, because endothermic reactions consume or absorb heat. We're just always trying to do the opposite thing that has been done onto the system. Okay. Now the third type of stress is changing pressure through volume. So I'm just going to do a quick review of what pressure represents and how these two variables are related to one another. So pressure in chemistry, the way we look at it, it is the number of times particles hit the walls of the container. So the more particles you have, the more hits you're going to have. The less particles you have, the less hits you're going to have. The smaller the volume, the more hits you're going to have. The larger the volume, the less hits you have. So if the number of particles go up, then the pressure is going to go up. Conversely, if the number of particles goes down, then your pressure goes down. Now, numbers of particles really relate to just the moles. And we can use the coefficients on a balanced chemical reaction as the number of moles in the chemical system. So that's part of the picture here. The other part of the picture is actually Boyle's law, which has a volume-pressure relationship. It essentially says this. If your pressure goes up, that's probably due to your volume going down. So if your volume goes down, you now have a smaller volume, smaller liters, but you have the same number of moles. So your number of particles is the same, but they're going to hit the walls more frequently. This is an inverse relationship. So pressure is inversely proportional to volume. Or your other scenario is, if the pressure has gone down, it's probably because the volume has gone up, and so it takes longer for the particles to hit the walls of the container, and therefore this causes the pressure to go down because hitting the walls is pressure. So if the pressure is increased on the system by, well, it's always going to be the opposite in terms of volume. So if I increased pressure, it must be because I decreased the volume, because they're always doing the opposite thing. If pressure goes up, volume goes down. If pressure goes down, volume goes up. Then the system will shift to the side with. Now, if the pressure is increased, we want to do a decrease in pressure. So we want less particles. So one more time, if the pressure is increased, the system wants the opposite thing to happen. They want the pressure to come down, which means we need less moles of gas. Okay. Conversely, if the pressure is decreased on the system by blank the volume, the opposite of decrease is increase the volume. Then the system will shift to the side with blank moles of gas. Well, if the pressure has been decreased, the system wants to bring that pressure back up. It wants to do the opposite thing. Well, how do I bring pressure back up? Well, I want to add more particles to the system. Now, because the system is closed, it just needs to shift to the side in the reaction that has more particles. Then it's going to hit the walls of the container more frequently and therefore bring the pressure back up. So this is going to shift to the side with more moles of gas. Now I've done that fairly quickly, and I know it's hard to understand something when you're just talking about it verbally and you can't visualize something. So the rest of this lesson, I am going to talk about each one of these in much more detail. I'll use some math to support it and give you some better visuals to understand. So if at this point you think, I don't understand what's going on, more clarity will be given to all three of these things. And just hang in there. This is a tough topic, but we will manage our way through it. Now, before we do that, I just want to talk about questioning and how it works and really what we're looking at here. Now, in any Le Chatelier principle question, you're really looking at three different variables that can be discussed, okay? So first of all, a stress has to be applied on the system, whether that's temperature, pressure, volume, adding or removing something. An initial stress to cause the equilibrium to shift has to take place. So that's one of our variables. Now, I assign each of the variables a color. So my stress variables are always going to be in red, and I use arrows to help me better understand and visualize what's happening. So all my red arrows throughout the lesson are all going to be about what the stress was in the question. Now, once I've applied a stress to the system, it's got to either shift towards the products or towards the reactants. That's your two options. It's a 50-50. You're either shifting to the left, shifting to the right, or actually I guess there's a third one. It just doesn't shift at all. Okay, but that is fairly rare. So all my shift arrows and my shift variable, I'm going to use blue. Now, as a result of the shift, the concentrations of the equilibrium system are going to change. So for instance, if I shift towards the product side, I now have more products, and so they have a new concentration which was higher than their previous concentration. And part of that is if I shift to the products and made more products, it must be because I consumed reactants, and so the new concentration of the reactants would go down. So the third variable, I use a green arrows to represent and green pen to write in. And again, any three of these things are going to be given in a question, and then one of the other two are going to be asked about. So really, you kind of have 6 scenarios, okay? You could be given a stress and you could be asked what was the shift. You could be given a stress and you could be asked, well, what happened to the concentrations? You could be given a shift and asked, hey, what kind of stress could have caused that? Or you could be given a shift and said, well, what happens to the concentrations due to this shift? Or you could be given the new final concentrations and asked, what kind of stress or what kind of shift would have caused this? So there's essentially 6 variations in questioning, as long as the question only addresses 2 of the 3 types of variables. So I suggest that you pick 3 colors to use. You don't have to use red, blue, or green. It could be, red pen, blue pen, black pen, or blue pen, black pen, pencil. But address each variable as a certain color and stick with that forever. Do not change that. Stick with whatever color coordination you want to use. And I ask that you do this, even if you don't like color coordinating. Some of the notes won't make sense unless you color coordinate the stress, the shift, and the new concentration. So please, before you continue on in this lesson, find yourself 3 colors that you are going to use. Okay, so here we go with our first stress. It's probably the easiest one to work with, which is changing the concentrations of a system. Now remember, an equilibrium system is a closed system, so normally nothing can get in and out of the system. So what we're doing is we're temporarily opening up some kind of valve, and we're forcing more reactant in, or we're forcing more product in, and then closing the valve off and allowing it to re-establish its equilibrium. So let's start with adding something into an equilibrium. So here is a equilibrium system. It's a very famous one, dinitrogen tetraoxide becoming 2 nitrogen dioxide molecules. And the stress, which I have in red here, is to add some N2O4 into the system. So what my brain says automatically is, what's the opposite of this? I mean, the opposite thing, which Le Chatelier's principle says, the system is going to do the opposite thing to counteract this stress. The opposite thing of adding in N2O4 is to remove N2O4. That's what the system is going to want to do. But keep in mind, this system is closed. So the chemicals aren't going to open the valve and let some stuff out. It has to try to figure this out on its own. It's got to figure out a way to decrease the concentration of N2O4 within its system. Okay, so let's think about this. If this goes up, I need to use it. I need it to come back down. Now, the only way I could do this is if these things start to hit each other more frequently, which they should because there's more of them, and therefore produce more of this. What that would do is decrease the amount of N2O4 and increase the amount of product. Now, how I visually show this is using arrows. I use red, blue, and green to represent a stress, a shift, and a new concentration. So for instance, I've added a bunch of N2O4 to this system. So I'm going to use a red arrow going up representing that I've added this in. So again, this is my stress arrow. Now, how can the system get rid of some of the N2O4 I added in? It can consume some of it. The only way it can consume some of it is if the N2O4s hit each other and produce product. In doing so, that would decrease this concentration and cause a shift towards the products. So I'm going to use a blue arrow here. This represents my shift. The system is going to react N2O4 molecules with themselves more frequently because there's a higher concentration of them and force the production of product. So in doing so, the concentration of the reactants and products are going to change. This is where my green arrows come in. So as these react more often, their concentration is going to come down. Now, it's not going to go past how much I added in because then that would be the opposite where you get out of balance again, but it's going to decrease it a certain amount. In doing so, I'm going to increase the amount of NO2. So this is going to increase in concentration. So these represent my new concentrations. I'm going to write NC, new concentrations. So one more time, because this is so fresh and so new, let me go through the scenario. I've added N2O4 into the system. There's too much of it. We got to get rid of it, but we can't open up a valve and just let this stuff out. So what this system does, because there's a high concentration of it, they react with each other more frequently, and therefore they start to form the product. So that's my shift. I'm shifting to the product side to decrease the amount of this reactant. Now, because it's shifting to that side, it means it's consuming itself. So the concentration of N2O4 is going to go down, and because it's producing NO2, this concentration is going to go up. So there's all three of our variables in this scenario: the stress of the adding, the shifting towards the products, and how the concentrations change. Now I'm going to support this with a mathematical concept. It's not going to work out in terms of exact values based on the mole-to-mole ratio, but I think it will help your understanding. So let's just hypothetically say this. K is equal to the concentration of the products over the concentration of the reactants. That is 100% true. That's not hypothetical. But let's just say that the ratio under the current conditions is we have 1 to 1 before we apply the stress. Okay, now what I'm going to do is I'm going to superimpose my arrows or some of them into this scenario. So let's imagine now we've added reactants, which is what's happened in this question. So my denominator has increased in size. And again, I'm just going to throw out a number. Let's call it 2. So now we're 1 over 2. So I've gone from having a K value, which is constant, of 1. It has now become a half. Well, a constant is a constant, everybody. It wants to get back to the value of 1. So what it needs to do is we need to shift the reaction to change these values, not so the ratio, that these values are 1 over 1, but they come up with a ratio that is equal to 1 over 1. Okay, so if I shift towards the products, I'm making more products. So in order to get this ratio back to 1, I could increase the numerator, and I'm using my green arrow here because this is what happens with the shifting. My products are increasing, or I could decrease my denominator. That will also allow me to get back to 1. So this could go down, which is happening over here. That is what's happening to my concentration. So mathematically, this is what I can do to get back to 1, and it's doing both of those things. So again, I know this isn't technically correct because I have a squared here, but we're just going to kind of make up values. So let's say the top increases to 1.5, and let's say the bottom decreases to 1.5. Well, I'm back to my k value of 1. So I'm going to do this one more time because we're so early on here. Okay, I add the stress, it causes the reactant concentrations to go up, and it throws the equilibrium constant off of what it's supposed to be. I'm making up a number saying 2. Now, to turn 1/2 back into 1 mathematically, you could do one of two things. You can make the numerator bigger, or you can make the denominator smaller. Now, in shifting to the products, it's actually doing both of those. It is making the concentration of the products higher, and it is making the concentration of the reactants smaller. Hypothetically, I just made up 1.5 over 1.5, and we're back to 1. We're back to our equilibrium constant of 1. Now, is there more stuff in the container? Absolutely. I've added stuff in, so there's more stuff. So rather than it being a concentration of 1 moles per liter over 1 moles per liter, it's now 1.5 over 1.5. But the fundamental nature of equilibrium and getting back to that constant is still there. It is 1. Now, you can also represent this graphically. So I'm just going to make up a couple of spots here. This isn't to scale or anything. But I hope it helps give some understanding. Okay, so I'm going to draw a flat line here, 2 flat lines, and I'm going to label the first one N2O4 and NO2. So this is a Le Chatelier graph, and when the lines are flat, we are at equilibrium, because the concentrations are unchanging. Equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction, and if that is happening, concentrations are not changing. The y-axis is concentrations. These things are flat. The concentrations are not changing. Okay, then we have our stress. We've added N2O4 to the system. So I'm going to use my red pen, and I'm going to go directly up. This is an instantaneously at addition of some N2O4, so its concentration is going to go up. It's gone up 2 squares. Okay, now what's happened is my ratio of products to reactants are out of whack. I need to make more products, and I need to consume the reactants to do that. So what will happen, and I'm going to use my green pen here because now the concentration is going to come down after the stress point. This is going to come down and flatten out as it reaches equilibrium. And this is going to come up and flatten out as it gets back to equilibrium. Okay, now this isn't done perfectly in terms of ratios. It's just a sketch. Technically the NO2, because there's a 2 to 1 mole ratio of them, it should move up double what the N2O4 is doing, but it's just a general sketch to give you an idea of how this works. So the flat line represents at equilibrium. I can put my red line in to represent the addition of N2O4, and then I essentially just do whatever my green arrows are doing afterwards. The N2O4 is going down and the NO2 is going up. So I've explained this question scientifically, and what I'm about to do is show you a bit of a shortcut to double check your answer. I don't want you to use this as the main way of solving the question, but as a way of supporting your answer that you get. It only works if you've been using the 3 different colored arrows, and you just have to follow a couple of rules. Okay, so these are the rules. If my stress arrow goes up, the system will always shift away from that side, and whichever way the system shifts towards, those concentrations go up, and whatever side they shift away from, those concentrations go down. So one more time, if my stress arrow goes up, I will always shift away. Whatever side my blue arrow points towards, my concentrations are going to go up. Whatever side it points away from, my concentrations are going to go down. Okay, so that's how it works for this scenario. Now, hypothetically, if our stressed arrow went up on this side, so if I added NO2, then I would shift the opposite direction. And then the concentrations this arrow is pointing towards would go up. And because it's pointing this way, the concentrations on this side would go down. It would just look inverted. One more time, if my stress arrow goes up, my shift arrow goes away. Whatever side I'm shifting towards, my concentrations go up. Whatever side I shift away from, my concentrations go down. And we will look at the opposite scenario in the next question. Okay, so in our next question, we're going to do the opposite of adding, which of course is removing. We're using the same equation, so we're familiar with it. So let's read the stress. NO2 is removed from the equilibrium system. So the system wants to do the opposite thing. Well, what's the opposite of removing NO2? It would be adding NO2 gas. Okay, so let's think about this. If I've removed NO2, the system wants to bring the concentration of that back up. The only way it can bring the concentration of that back up is by shifting towards that side and having the N2O4 react with itself and produce more NO2. Now this would cause the concentration of NO2 to go up, and this would cause the concentration of N2O4 to go down. So if I remove something, I always want to shift towards that side to make more of it. In doing so, the concentration of that thing will increase, and the concentration of the substance on the other side has to decrease because it's being used to produce that substance. So when we were doing my mindless Mr. Hope backup way, on the previous question, it was all about if the stress caused an increase. Well, in this case, it's causing a decrease. So this is the way we can always back up our scenario. If our stress arrow goes down, we always shift towards that side. Now, whatever way we shift towards, and this was true in the previous question, the concentrations on that side will increase. And if we shift away from this side, its concentrations are going to go down. So again, if the red arrow goes down, we shift towards. Whatever side the blue arrow shifts towards, our concentrations go up. Whatever side we shift away from, our concentrations go down. This is the opposite of the previous question. Now I'm going to quickly prove this with mathematics. We're going to stick with K is equal to products over reactants. We're going to stick with the fact that it's 1 over 1. Now, my stress is to remove products, so I'm decreasing my numerator. Now the only way I could bring this back up to a ratio of 1 over 1 is one of two things. I could increase my numerator, I could bring it back to 1, or I could decrease the denominator, or I could do a bit of both. So let's just make up a hypothetical number. Let's say this decreased to 0.5 moles per liter over 1. We're back to a value of 1/2. Now, what the system did is it shifted towards the product side to make more of these products. which is on my numerator. So my numerator increased. That's going to help me get back to 1. But in doing so also, I've decreased the amount of reactant, which is going to be on my denominator. So mathematically, I've done the two things that's going to help this get back to 1. So I'm just going to make up a couple of values. Let's say this on the numerator goes up to 0.75 moles per liter. And on the denominator, it's 0.75 moles per liter because it decreased. Well, my ratio is still now back to 1. Yes, overall, the system does have less stuff, but the ratio of products to reactants is still the same. Graphically, the way this would look, I'm going to stick with the same two lines. I've got N2O4 on the top, and I have NO2 on the bottom. So at my stress point, I have my line going down. Okay, so this goes down. Okay, I've decreased it. Then I get a shift to get the equilibrium system back to equilibrium. This causes the NO2 to go up. So I'm going to superimpose that on the graph here. So this goes up. That's what my green arrow is doing. Now, I would never go past my starting point like this. I would never get back to it. It would never work out mathematically because there's less stuff. So it's got to be somewhere kind of in that region. And then my N2O4 has to decrease because it's being consumed. So I'm going to have it come down like this. And so that's what its green arrow is. So this drop is the stress. It's showing that this is going down, and then how the graph recovers is what my green arrows are doing to get back to equilibrium. So this chart summarizes my way of double checking your work using the arrows. So I think you should pause the video now and copy it down, and then I'm going to do a little quick review of it, of how it works, because I'm going to continue to use this method to support my answers. So pause the video now and copy out this box. So now that you've had a chance to copy that out, I'm just going to do a quick review. So I'm just going to hypothetically make up a equilibrium here. Let's say it's A is in equilibrium with B. And I'm going to run kind of through our scenarios, okay? So here's our first scenario. If my stress arrow goes up, okay, if my stress arrow goes up, so let's say I added A, then what's going to happen is the system is going to shift away from the stress. So I would shift this direction. Now, whichever way I shift towards, those concentrations are going to go up. So that's what it says here. New concentrations go up on the side that the shift arrow points towards. So because this blue arrow is pointing towards the products, it's going to go up. And then underneath, it says the new concentrations are going to go down on the side that the shift arrow points away from. So this is going to go down on this side. So there we go. Stress goes up, shift goes away. Whatever side I'm pointing towards, my new concentrations increase. Whatever side I'm pointing away from, my new concentrations decrease. Here's the next scenario. I increase the concentration of B. This is scenario 2. So if B goes up, I have to shift away. So I shift to the reactant side. Whatever side this points towards, the concentration has to go up. Whatever side my shift arrow points away from, the concentration goes down. So there are your two scenarios for a stress increasing something. So what I'm going to do is I'm going to erase those. I don't want you to erase them. I'm going to erase them. And then we're going to go through the two scenarios of stress causing something to come down. Okay, so here's scenario 1 with removal or stress causing something to come down. If I remove A, I need to increase the amount of A. So the only way you can do that is to shift the reaction towards A to produce more A. This is going to cause the concentration of A to go up and B to go down. So if my stress arrow goes down, the shift arrow moves towards the stress arrow. This could be left or right. In this case, it's left. Whatever side my stress arrow points towards, so whichever side my shift arrow points towards, the concentrations are going to go up. And whatever side it's pointing away from, those concentrations are going to go down. This concentration is going to go down. So that's scenario 1 where my stress arrow goes down. Here's scenario 2. B is removed. Now, because my stress arrow goes down, my shift arrow has to go towards that side. So I'm going to shift towards the product side. Because I am pointing towards the products, I'm going to have an increase in products. So my green arrow points towards the products are going to increase. Whatever side I shift away from, those are going to decrease. And there's our 4 scenarios that we can use to double check our work to make sure we've done it right. That doesn't require too much thought. So for our next stress, we're going to look at heating and cooling. And this should go a little bit faster now that we have the basic idea of what Le Chatelier's principle is. So the first thing we're going to look at is an endothermic reaction. We're going to look at heating it and cooling it. And we're going to look at exothermic reactions, heating and cooling it. So essentially 4 scenarios. So just as a quick reminder, endothermic reactions will either have heat written or energy or a value written on the reactant side, or will be written out as an enthalpy value as being positive. So if it was delta H notation, it might, instead of having heat written on the reactant side, it might have something like delta H is positive, and I'm just making up a number here, 50 kilojoules. Okay. Now, if I was given a question where I was given delta H notation, I would then convert it into this type of equation where I write energy into the equation as a term. That's called a thermochemical equation, because it allows me to use the arrows to back up what I'm doing, okay, or to double check what I'm doing. So obviously, if you heat something, the opposite is cooling, and if you cool something, the opposite is heating. So in general, if I cool the system, the opposite thing would be to heat the system, and in order to heat the system, it would have to perform the exothermic reaction. If I heated a system, then the system wants to cool itself, and the way it could cool itself would be to perform an endothermic reaction, because that would absorb some of the heat that was added to the system. Now, realistically, when you change the temperature of a system, you're changing the kinetic energy of the system and how the particles are hitting each other, and this actually does change the K value. This is the only scenario where the K value actually changes, and we are going to have to look at how does a K value change here in terms of just increasing or decreasing, but not in terms of an actual numerical value. All right, so let's start with our first question here. We're adding heat to the system, okay? So if I'm adding heat to the system, the opposite would be to cool the system. And the reaction that would allow us to cool the system would be to do the endothermic reaction. Now, the endothermic reaction, based on the way that this equation is written, would be the forward reaction. Because energy is written as a reactant, the forward reaction would be the endothermic reaction. So the system would have to shift to the product side to do the endothermic reaction to try to decrease the temperature of the system. In doing so, if I shift to the product side, the concentration of the products are going to increase, and the concentration of the reactants are going to decrease. Now, I haven't added in my red arrow here, but I'm going to do that right now. So here's my stress. I've added heat to the system. If my red arrow goes up, I want to shift away, which it is. Whatever side I shift towards, those concentrations are going to go up. Whatever side I shift away from, those concentrations are going to go down. So I've done it both ways. I've explained it scientifically, and I've also used my arrows to support my answer. Now let's talk about how K would change. And this is a really easy thing to do in order to figure out whether it's going to increase or decrease. All you do is you write K is equal to, and I grab my green arrow pen because we're going to be using those arrows to figure this out, is products over reactants. Now, if I shift to the product side, the amount of products increase and the amount of reactants decrease. Now, let's think about this mathematically. If my numerator becomes bigger and my denominator becomes smaller, overall the number has to go up. So this would be an increase in the K value if this is raised in temperature and held at that temperature. So for instance, the system is in a glass vial that's closed off, and I put it in a hot water bath, and the hot water bath is set at 80 degrees Celsius, and it's just left in there at 80 degrees Celsius. We will get a shift, and then that shift will be maintained to keep the concentrations at a certain level, but overall the K has increased because we have increased the kinetic energy of this system the way that it is set up. Now, how does this look like on a graph? Okay, so let's stick with N2O4 here, and let's stick with NO2 here. Now, because heat can't be given in an instant, it's just not like you can turn on your oven and it goes 25 degrees to 400 degrees. The concentrations change gradually. We don't get this sharp vertical line like we did when we added something in or when we removed. Okay, we had a sharp vertical line. I put in my red line. Here, there's going to be none of that. The lines are going to begin to curve the way that the green arrows indicate. So for instance, the concentration of N2O4 will gradually come down, and the concentration of NO2 will gradually come up, and then it will level out once they've reached and maintained that temperature, and that's what it's going to look like. This does permanently change the K as long as that system is maintained at that temperature. So a heating and cooling Le Chatelier graph are always smooth curves. And the smooth curves align with my green arrows. Green arrows. Good. Okay, let's try the next one. I'm going to zoom in over here. Okay, removing heat from a system is really saying the same thing as remove heat is the same thing as cool. All right, so there's our stress. We remove heat from the system or we cool the system. For instance, ice bath. Well, the opposite of cooling, of course, is heating. And if I want to heat the system, it needs to perform the exothermic reaction. Now, the way that this equation is set up, the reverse reaction is the exothermic reaction. So by performing the exothermic reaction, heat would be released. It tries to bring the heat of the system back up. It tries to warm the system back up, and so it's going to shift in that direction. Because it's shifting to the reactants, we're going to end up with more reactants, and because we're shifting away from the products, we're going to have a decrease in products. Now, I haven't superimposed my red arrow yet. I'm going to do that now. So if I'm cooling, I'm removing heat. And so let's double check how this works. If my red arrow goes down, I shift towards. Whichever side I shift towards, my concentrations go up. Whatever way I shift away from, those are going to go down. So that's supported. Let's figure out our K value. So K is equal to products over reactants. I put my green arrows in, so my products are going down, my reactants are going up. Mathematically, if your numerator is getting smaller and your denominator is getting bigger, overall the number is getting smaller, and so there's going to be a decrease in the K value. Okay. Now, another way you can do it, if you really struggle with fractions and you don't quite understand what's going to happen to the K, just do this. Whatever the arrow is doing on top of this fraction is what's going to happen to K. So if the arrow is going up on my K here, then the K is going to increase. If my arrow is going down on the numerator, my K is going to decrease. Let's put this into graphical form. I have N2O4 at equilibrium. It's a flat line. I have NO2. It's at equilibrium. It's a flat line. And so when I look at this, my product is NO2. It's decreasing. So this is going to go down. And my N2O4 is increasing. This is going to go up. And what you'll notice is when it reestablishes equilibrium, and what I mean by that is when these lines become flat again, it's back at equilibrium. So we're back at equilibrium about here, they've leveled out. We're back to equilibrium here, we've leveled out. What you'll notice here is the gap between these lines is much closer, and the gap between these lines is much bigger, and that's telling me there's such a drastic change in concentrations that the K values are going to change. The last type of stress we're going to look at today is a pressure volume change. Now, at the start of the lesson, I talked about how pressure is inversely proportional to the volume of the container, which simply means this. If the pressure doubles, it's because the volume halved. Or if the pressure halved, it's because the volume doubled. It's inverse in what it does. So again, for instance, if I quadrupled one, it would be a quarter for the other. If I tripled one, it would be 1/3 for the other. So this is all based around Boyle's law. The other thing we discuss is what actually is pressure when we talk about pressure in chemistry. Pressure is the number of times particles hit the walls of the container. More collisions with the container, more pressure. So if I have more particles, more pressure. If I have a smaller volume, more pressure. So if the number of moles increases, the pressure is going to increase. If the number of moles decreases, then the pressure is going to decrease. All right? So more particles means more pressure, and less particles or less moles means less pressure. The other thing you can do is you can change the volume of the container. So looking down here, we can see both of these boxes have 5 particles in them. And you can see that if you have a larger volume here as opposed to a smaller volume here, it is more likely that these particles are going to hit the walls of the container because they have less distance to go to hit the walls of the container. Therefore, the pressure would be higher here even though they have the same number of moles. Conversely, on this side, these particles have a much longer distance to travel in order to hit the walls of the container. So now the pressure here is going to be less and in proportion, inversely proportioned to the volume. So I think this is a good visual representation of how volume would change the pressure of the system, even if the number of moles were held constant. Now there are some things I do in order to help me answer these questions. And the biggest ones are making sure that we count up all the gaseous moles on both sides of the equation and getting rid of any solids or liquids because they aren't going to cause the pressure, only a gas would. I always convert a pressure stress to a volume stress. It'll help me with my hope way of getting an answer. And I always keep this in the back of my mind. If the volume is increased, so more volume, then there's going to be room for more moles of gas, and we're going to shift to the side with more moles of gas. I always keep this in mind as well. If there's a smaller volume, then there's less volume for gas, so we're going to shift to the side with less moles of gas. That's kind of the Mr. Hope way of kind of knowing what to do, even if we're not 100% sure on what's happening. Okay, now number 6, I'm going to spend a bit of time on it. This one is often glazed over in a lot of lessons for this stress, but understanding how to do the graph here requires an extra step. So let's start with this first question. First of all, it says the stress is that pressure is increased. What I immediately do is write what happened to the volume, which is the exact opposite of what the pressure did. So if the pressure is increased, then I automatically know that the volume is decreased. And I will write that in immediately. So pressure goes up, volume goes down. Okay. The next thing I do is I highlight all the states. I make sure they're all gases and it's a homogeneous mixture. If there is a solid in there or a liquid in there, I cross it out. Their moles do not count towards the overall moles on either side of the reaction. Then I count up the number of moles on either side. So over here, I have 1 mole of CH4, 1 mole of H2O, so there's 2 moles of gas. On this side, there's 1 mole of CO and 3 moles of H2, so there's 4 moles of gas. Okay. Now, if the pressure is increased, we want to do the opposite thing. So if the pressure is increased, the system wants to decrease the pressure. So this wants to make the pressure go down. All right, if I want the pressure to go down, I want to shift the side with less particles. Less particles means less collisions. Less collisions means less pressure. So I'm going to shift to the side with less particles to decrease the pressure inside of the container. In doing so, I will increase the concentration of these two while consuming 4 moles of these two. Whatever side I shift towards, those concentrations go up. Whatever side I shift away from, those ones go down. Now, I cannot put a red arrow on this scenario because a volume isn't part of the chemical equation. I will use a red arrow later, but it's impossible in this scenario. So what I'm going to do before I move on is I'm going to show you another way of answering it. Okay, and this is the other way. I focus on the volume and I simply say, if the volume goes down, then the number of moles needs to go down. If the volume goes down, then the number of moles needs to go down. Less room for less moles. So because the volume is decreased, I'm going to shift to the side with less moles. There's less moles right here. Which way did we shift? We shifted that direction. So whether I use the concept of pressure and particles to tell me which way I'm going to shift, or volume and which way I'm going to shift, I'm going to get the same answer. Now, the hard part here is really graphing. Now, in order to figure what happens in a graph, there's 2 parts to it. We got to figure out what happens at the stress point, and then what happens to try to get back to equilibrium after the stress point. We already know what's going to happen after the stress point. The concentrations of the two reactants are going to go up, and the concentration of the two products are going to go down. These green arrows tell me what happens after the stress has been applied, not at the stress point. So for example, when I look back to here, at my stress point on this question, I removed NO2. This here, this line going straight down is telling me what happens at the stress point. The green arrows tell me what happens after the stress to get back to equilibrium. So when I relate that now to the question we're currently doing, I know what happens after. I don't know if my lines go up or down or both, or is there any kind of vertical stress point? So that's what I'm going to teach you now. How do I know what happens at the stress point? Okay, so I'm just going to make up, again, some lines. This is fairly arbitrary. I'm just going to start with the reactants on top for no particular reason. I'm just going to call this CH4, H2O, CO, and H2. Now, normally your lines are going to change in proportion with the coefficients. I'm not doing that here. I'm just kind of giving us a general idea of what's happening, okay? This is just a sketch. This isn't to scale in any kind of way. All right, so these are all in equilibrium now. They're all flat. What happens when we have a pressure increase, volume decrease? What should happen to all of these lines? How I do that is the following. We're dealing with concentrations here, and we have a volume change. So using the C is equal to N over V equation, which is for concentration, which is what is on this graph, I simply assume that immediately when the stress is placed on the system, we haven't had a shift, so the number of moles is held constant. I'm not changing this in any way. But the volume is. So the volume was decreased. So let's think about it. If my denominator becomes a smaller value, so let's say we had 2 over 2, and now we're 2 over 1, my value overall for concentration goes up. If your numerator is held constant and your denominator gets smaller, overall the value goes up. Example, let's say I started with 2 over 2, that's 1, and then I stuck with 2, but then it became 1 on the bottom, well that's 2. I went from a concentration of 1 to a concentration of 2, which means my concentration has gone up. So what happens at the stress point is all of the lines are going to go up because that represents concentration. Again, the y-axis is concentration. At the stress point, all of them increase because we have the same number of moles but in a smaller volume. Now what happens after this stress point is what we're doing with the green lines, okay? So everybody, the CH4 would go up. I know I'm coming off my sketch. It is just a sketch. My H2O goes up, but my CO and my H2 come down. So I'm just going to have them come down a bit like that and come down a bit like that. So at the stress point, the red is the stress point. When the volume is decreased, all the lines go up. So if the volume goes down, the concentrations go up at the stress point if we're trying to interpret a graph, which is something that you will have to be able to do. So let's get you to try a question. I would like you to pause the video and give B a try. I would like you to do your red, blue, green arrows. I would like you to do how the concentration changes at the stress point. and then we can graph it together. So please pause the video at this time and try to answer question B. Okay, now that you've had a chance to give it a try, let's work on it together. So the question says that the stress was that the volume is increased. So I immediately put in what is going on with the pressure. So if the volume was increased, then the pressure must have decreased. That's what happened at the stress point. Now, what is the opposite of volume increasing? If the volume was increased, the opposite would be to decrease, and the opposite would be to increase the pressure. This is the opposite thing, and this is what the system will try to do. Now, if it can't change the size of the container, which it probably can't, it's going to adjust the amount of moles available. So let's think about this. If I want the pressure to go up, I have to shift to the side with more moles of gas. So let's count those up first. On this side, I have 1 mole of N2 and 3 moles of H2, so that is 4 moles of gas. On the other side, I have 2 moles of NH3. I double check, they are all gases, this is a homogeneous mixture, I'm going to continue on. So if the volume is increased, the pressure is decreased. I want to do the opposite. I want to bring the pressure up. I'm going to shift to the side with more moles of gas. Or, everybody, I can think about it in terms of volume. If the volume has been increased, then there is more room for more moles of gas, and I'm going to shift to the side with more moles of gas. And sure enough, I am shifting to the side with more moles of gas. So I've answered the problem in 2 ways. I've used pressure. Because the pressure went down, I want the pressure to come up. In order to get the pressure to come up, I need more particles. I shift to the left. And the other way was with volume. I've increased the volume. Now there's more volume for more moles of gas. I'm going to shift to the side with more moles of gas. Both ways of answering the problem are correct. The pressure way is a more scientific way of explaining what is actually happening. Now, whichever side I shift towards, I'm making more of that substance. So I'm making more H2, I'm making more N2, and whatever side I'm shifting away from, I'm using up, so the amount of NH3 is going to go down. The next thing we should do is look at what would happen at the stress point on a graph. Well, concentration is equal to moles over volume. If at the stress point we haven't shifted yet, it's just instantaneously, our moles are going to be constant. What happens to the volume? Well, the volume has increased. So what's going to happen if my denominator becomes a bigger number? If your denominator becomes bigger, your value overall goes down. So let's use some imaginary numbers here again. Let's say originally it was 2 moles in 2 liters. It's still 2 moles, but now let's say it's 4 liters. Well, 2 over 4 is a half, whereas 2 over 2 is 1. The concentration of everything went down. That's at the stress point. So let's write this in on the graph. Again, completely arbitrary here. I'm just going to make 3 lines. We'll call the first one N2. The second one H2, and the last one NH3. This is not to scale in any way. At the stress point, all of my arrows need to go down, or all of my lines need to go down. So down, down, down. After the stress point, I got to do my green arrows. So the NH3 has to continue to go down and flatten, whereas the H2 is going to come up and flatten. Make sure you're not coming up past your original concentration. That wouldn't work. It's got to be up, but below your original concentration. And I'm going to do that as well with the next one. Up, but below my original concentration. Once these all level out, and they should be leveling out together. Let's say they all leveled out here. we have reached equilibrium and we are back to where we were at the start. So remember, if the volume goes up at the stress point, then the concentrations will all go down at the stress point. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.